Hi guys, I'm Chris, and today we will be finding the Thevenin and Norton equivalent of two circuits. The first one will be now the basic idea here is that we're going to reduce this circuit at these two nodes into one equivalent voltage source and one equivalent resistor for the Thevenin equivalent, or one equivalent current source and one equivalent resistance for a Norton equivalent. Now let's get started. First, we're going to write down the definitions. We know that V Thevenin is equal to the open circuit voltage, and that I Norton is the negative of the short circuit current going in. This is the open circuit voltage, and if we imagine that these dots are connected, this is the this is the short circuit current going in, and therefore I Norton is the short circuit current going out. To find our Thevenin or our Norton, we simply take the ratio of the open circuit voltage over the negative of the short circuit current going in, or just I Norton, The simplest way that I found to solve this problem is by using nodal analysis. We're gonna use Kirchhoff's current law at node A. And Kirchhoff's current law tells us that the current flowing in is equal to the current flowing out. And because this is an open circuit, we know that no current comes out through here. The current going in at this node is equal to I naught, and the current going out is equal to the voltage at this node minus the voltage at this node, which is simply ground, over R2. So we have I naught is equal to the open circuit voltage, because that's the voltage at this node, over R2. And since V Thevenin is equal to the open circuit voltage, we have V Thevenin equals I naught times R2. Now to find I Norton, we short circuit the open circuit, and we notice that this node and this node are one and the same, and therefore there's no voltage across this resistance and no current flows in because of that. So the current coming in, I naught, equals the current leaving by Kirchhoff's current law, and that just tells us that I Norton is equal to I naught. And now we find the Thevenin and Norton resistance, which is just the ratio of the open circuit voltage over the negative short circuit current going in, and that's just I2, R2. A second way we can use to find the resistance is by finding A second way we can use to find the Thevenin resistance and Norton resistance is to find the resistance looking in. And I've actually written a few notes on this so you guys can take a look at it. I'll pull it up in a second. This is the process that we need to take in order to find the resistance looking in. First, we have to kill all the independent sources. We replace the voltages, DC or AC, by short circuits, and we replace the currents, DC or AC, by open circuits. Then we apply a test current and a test voltage to measure the resistance. Now back to our problem. To find the resistance looking in, we replace the current source by an open circuit. We use Kirchhoff's voltage law around this loop because no current flows into this way. A simple way to remember this is that current is marked. It knows that it has no way to go, so it finds a way to loop back on itself. Kirchhoff's voltage law tells us that the voltage rise equals the voltage drop around a closed loop. So we have V test is equals to the voltage drop here, which is just I test times R2, and I test is I test. So to find the resistance, we take the ratio between V test and I test, and that's just simply R2. One thing to notice is that we could have done all this by inspection without having to write any of it down. The resistance looking in is clearly just the resistance across these two nodes, which is just R2. If this was helpful, please make sure to smash that like button and subscribe. I'm be sure to be posting more videos like this.